Log on, tune in, find out. Another good idea from Cambridge.
Art Richmond and statistician from Brown University, Crystal Linkletter. And this was published, should I start actually? I'm just, yes, this was published in this journal called Geoscientific Model Development that I want to advertise because it's open access. So everybody can read that, these papers. You have to pay to publish a bit if you have the means to. I think it's like all these EGU journals. And it's a venue for our research. All of us that are at the intersection of atmospheric or geophysical sciences and statistics or other areas. So this work started when John T. and I visited the Statistical and Applied Mathematical Sciences Institute in North Carolina, SAMC. So it's NSF funded. I think I can. So Robin yesterday gave a talk about emulation of a complex computer model, which was a climate model. Here it looks appealing, GCM, because you may think it's a global climate model, but it's only a general circulation model for the ionosphere. Anyways, I want to introduce those techniques and go further, since I want to engage with you in those topics, and probably there's interest over this semester in dealing with climate models in that way. I'm sure there is, because I've seen your work yesterday. So I'm going to start with the toy example and then talk about this particular model, the observations, the methodology, some results, and advertise another work by John T. Which is on the better emulation. So the toy example, to present the calibration, so just to tease you a bit, so we're here looking at an idealized computer model. So instead of looking at a complex computer model, we here focus on this function. So it's just a function. You see you have x. X is here a parameter that's supposedly controllable. But by that I mean it's given. It's not it's the setting from Kennedy and O'Hagan and all these nice studies. So controllable means it's fixed. You can control it sometimes, or sometimes it's given. Think time, for example, or location. An unknown parameter theta, that's the parameter we are after. It's a parameter that changes the output of the model, obviously, but you don't really know what is the value. You would like to know more about that parameter. So here, this is this function, very simple function. And the true value I set here in this example was 0.3 for theta. So the idea is to exercise the computer model at a set of potential values for theta, and then look at the difference, or examine the difference between the outputs given by these theta and the observations given by some of the outputs of the, not the outputs, sorry, the observations given by measurements. And you want to match the observations with the computer model output. So x here for the here it's assumed to be 0, 1. It could be something different. It's just a specific setting. So here some design. Usually x, you think of time, it's given, but here I put it in the x-axis. No surprise, and the thetas are there. So we try to sample as much as possible. I go back to that, and yesterday Robin presented some Sobol sequences, but here we did some Latin hypercube. As a result of this sampling, we get those crosses. These crosses are model outputs for, on the x-axis, this value of x, which is controllable or fixed, okay? And on the y-axis, you have the output of the model, these crosses, okay? The observations, here we have 30 observations, are nicely along the computer model. It's not very noisy, actually. It's not noisy here. It's idealized, very idealized situation to motivate the problem. So you see, with different thetas, these functions sine 5 pi theta x, the outputs are all over the place, right? Maybe here this cross matches this circle, and you may think, oh, maybe that's the right value, but you know, there's a lot of uncertainty in all of this. But we want to find theta equals 0.3. And this technology is using a Bayesian approach. That means that we consider the uncertainties given by the parameters and hyperparameters in description of the whole covariance structure, etc. So we have a lot of uncertainties. I will come back to that. But anyways, let's see the result. So if we run an MCMC, a Monte Carlo Markov chain Monte Carlo works fine too. We explore the input parameter space. So we try to find in the parameter space the thetas that will help the computer model match best the observation. Okay? And we collect the values along this path of this Markov chain. Okay? So as a result, if we collect enough values, we have a sample we can draw from that posterior, and we have a sample, and we can plot an histogram. And this is the histogram just running that very simple example here. For theta is the parameter we are after. Theta was supposed to be 0.3. Unfortunately, in this very simple example, obviously, we retrieve that value as kind of the mode of that distribution, posterior distribution, with some variability. Little variability here because the example is unidimensional. There's not so much noise, etc. So that's to motivate this calibration issue. I can show you also, as a result of that, an emulator or a prediction. Actually, here is the combination of an emulator and some bias. I'll come back to this. So this is the uncertain prediction because there's uncertainty in the theta itself, and there's uncertainty in the associated parameters. So as a result, you get some confidence bands. So I repeat myself here. The circles are the observations. The line is the sum of the emulated computer output given by statistical surrogate of the computer model, along with its uncertainty, with a bias too. The model could, here's not the case much, but could have some bias. The observations, the model can have some abilities to predict a particular output, but there still could be some bias due to deficiency in the science or things like that. So again, this is to advertise this model, this whole setup, because in this very simple example, this toy example, it works fine. There's reason to believe that it works fine in many examples and theory as well. So let's go to this key application, the TIE-GCM. So it stands for Thermosphere-Ionosphere Electrodynamics General Circulation Model. And here you see, I hope, a magnetic storm and magnetic activity in the ionosphere. And this has some consequences on the telecommunications, usually. So it's very important to study. I think in the climate model CCSM, the NCAR climate model, there's an element of the ionosphere there too. Depends on the on which level you select. Anyways, it's the NCAR model for this, and it's designed to calculate many things, but the dynamics, chemistry, energetics, electrodynamics, only above about 100 kilometers, up to 500. I think that above that it's the magnetosphere. I think they have a model for the magnetosphere as well, if you remember, Jonty. I think a very nice one. But this is just for this model. There are many input parameters to be specified. So at the lower and upper boundaries, number of uncertain internal parameters. So the scientists, when they run this model, they just run it at a certain set of input parameters, and they believe that reasonable choice, but they want to know more. They would like to know more. So here in this particular paper, we selected one output, the response of the eastward magnetic perturbation on the ground, at the ground. So it's called mag-GRD-D, and there are several of these. There's DH and something else in nanotesla. So we look at one output only, okay, and we're to compare the outputs with the runs of the model and find the calibration parameters of the model that may be of interest. So there are some issues here. This particular output varies from hour to hour during the day, with season, solar cycle, location. A lot of things here. It's caused by electric currents flowing in the ionosphere. That's the mechanism. So there's some problem here in terms of what do we compare to. There's so many instances. So we simplify this. I mean, the scientists actually were driving this study, obviously, and they selected the equinox and some very quiet time. So this is the locations where observations can be retrieved. I don't exactly understand how they do it, the particular mechanism, but it's spread all over the world, roughly, not too much over there, but we wanted to try our methodology on two locations that are different, so we selected two, Apia and Odessa. Apia is about -15 south, roughly, and Odessa 45 north or so. So we expect different types of outputs, and actually it's the case. And we hope that that our study will be consistent for those two locations. So two locations, Apia and Odessa. So Apia on the left, Odessa on the right. It's going to be like this for the whole talk. So here I'm cheating a bit. The outputs of the model, those crosses, and the observations here were transformed. We didn't get this nice these values like this. We had a lot of variability, a lot more variability actually on the side. The high values and low values. We have to dampen that. I'll talk about that later. But here you see again the observations. It's every half an hour, also. And the
what is plotted? What kind of quantity?
Oh, this quantity, this mag-GDDR. It's a magnetic. Okay, let me go back to this. Sorry, I'm not the scientist. So magnetic is what perturbation of the ground in Tesla, nanotesla. So
Yeah, perturbation in that.
yes, you understand better than me.
Oh.
Little bit more. At least it makes sense to you. So at the bottom is the hours of the day, and the local time, by the way. And the observations are those circles in Apia. And in Odessa, it's actually kind of the opposite variation here. Maybe it's, I'm pretty sure it's because it's north and the other one is south. So when you try to run the model with different parameters, here we have 30 runs. With different parameters, we get this spread. Okay. Maybe this cross here will match better this circle. However, I wouldn't go that far because maybe this cross in the middle, that cross in the middle, I should have put some lines across, with some additional bias would reflect better the variability of the observations. Who knows? If there's a shortcoming in the model. Anyways, there's obviously some bias here, and there's some difficulty in reaching the observation. Anyways, we can try to aim for some parameters that will help the model reproduce the observation. So again, what's driving this, and maybe you understand better, the atmospheric tides. So these are waves of periods that are harmonics of 24 hours. Here we select, we considered the 12 and 24 actually. It's very difficult to define since the observations are limited, the tides vary. That's the issue. And the goal is modeling this tidal propagation better and look at the distribution. So that's the goal. So how do the scientists go about this? They have some inputs for these tides, and obviously since there are tides, there's some amplitude, local time at which it maximizes, a phase parameter, and some other quantity which is this electron number density. So amplitude and phase. And it's at the lower boundary. So that drives obviously the waves. Okay. So that's interesting. The scientists told us, well, we don't know much about this amplitude. We just know that it should be in that interval. The phase, it should be in that interval. But one problem was that 12 is equal to 0 for us. I mean, it's, having 12 or 0 phase, it doesn't matter. And we'll address that. And this is quite straightforward, more straightforward parameter. So we have amplitude and phase. Another problem is that when amplitude is 0, you cannot determine the phase, really. So that's another problem. Anyways, so the phase is periodic, as I wrote down here. So we came up with this alternative parametrization of these initial parameters to run the study on those parameters, and then we go back to the parameters that make sense for the scientist. Okay, so this parametrization is just a one-to-one way to reparameterize in a meaningful way for the computer, for the technique, because there are many issues with the covariance structure, etc. It's difficult to model periodic things, but the electron density is not reparameterized, it's just standard. So again, I'm repeating myself here, but those two locations, so it's 13 and 46 roughly, and it's we're going to consider runs of the computer models for those locations. I mean, I showed you already some runs. And how do we run those runs? I will explain just later, but the observations and the simulator outputs are transformed as I presented earlier. This is the transformation of the output, so this kind of a log transformation that Jonty came up with, actually. You tried several, right? To dampen the variability, so that the variability is constant in time. Roughly constant in time, it's not too wide. And now I'm going to present the methodology, and the methodology is not mine, it's definitely Kennedy and Huygens and others that came up with this methodology. And there's an entire, I would say, research project called MUCCOM in the UK, Managing Uncertainty for Complex Model, that even has some web pages, toolkits, etc. that explain that better than I can do. Anyway, so if you put prior distribution on the calibration parameters, so what is that? You say, I know something about those parameters, say the interval on which they lie, but you can say even more, which would be, for example, well, they're more likely to be at those values if you have a better idea of their distribution. So that's your prior information as a scientist. And then you let the information containing the data update these a priori assumptions, that's the basics of Bayesian statistics, and to get a posterior distribution of the calibration parameters. But there's a lot of machinery in between. Okay? Even the data can sway your opinion entirely, I mean, if possible. And a set of inputs, I'm sorry for the disagreement in notation with the toy example. In the toy example, my x was the time t. But here, I put together the controllable parameter or the given parameter, not an unknown parameter, which is here is time, those 0 to 24 hours, and theta, which consists of the three parameters that are unknown, which were amplitude, phase, and electron density, but reparameterized because it was easier. So again, first category is the known parameter, here the time, and the unknown calibration parameter. But the computer model has to be run at those for those parameters, right? Inputs. So we denote by eta the output of the computer model. Here this mag D type. And then TIE-GCM is run at inputs in a design, so choice of values. We design of the model is denoted dm. And the field data, there's the observations, IYF of t. There's no theta in the observations because theta, Mother Nature knows what is theta. And they're collected at the number of inputs in the design df. So a number of times. They actually don't match here, the times at which you run the model, at which you collect observations. So this is the design. So this is, unlike yesterday's presentation, it was Sobol sequence, which is more of a sequence that is deterministic in some way. Here we went for the Latin hypercube, which tries to, the maximin option, which tries to maximize the minimum distance. So try to sample in that space, this three-dimensional space, as much as possible with only a few runs. To be honest with you, we didn't do very well.
This was a terrible design.
It's mine, actually. I'm sorry.
we're both guilty of this design.
Well. You'll see why, because here this is kind of a hole here, but that's actually the region of interest. Mostly.
We've got multiple repetitions at zero values of amplitude across phase, which is stupid. When amplitude is zero, phase doesn't matter.
Yeah.
And we have mechanical back to phase periodic.
Yeah, we accounted for it, no? Yeah.
Not in the design.
Not in the design. Yeah, yes, exactly. Yeah. So the design, I'm guilty, and we have to work on this and more. Anyways, okay, let's say it's reasonable at first. It worked okay. It's not too bad. So the computer model, again, it depends on the parameters t and theta. What's the main assumption is that the computer model is an approximation of the reality, we hope. So reality is not field data, actually. Reality is field data with some noise. I will put down the equations just in the next slides. The observations are collected at a number of inputs in the design. I'm repeating myself here. So here, precisely, the time points of observations here were 14 minutes past midnight, etc., for Appia, and 43 minutes for Odessa. And they don't match actually what the model outputs times are. And again, the design of experiment for the parameters. So the goal is to cover as much space as possible. We don't only 30 runs because again it was run at NCAR supercomputer. It's faster than the climate model. It was just 10 minutes, I think. But still. The time components, we chose 12 points every other hour. That's a decision that I made for to get kind of the shape of it almost right. And the time points are different, as I said, but the technology accommodates that variation. And the Bayesian formulation of that problem, which is from the seminal papers by Kennedy and Hagen and JRSSB in 2001. So there's a bias. So there's both a bias between the computer simulator and the physical observations, delta t. So here the reality is the model outputs at the same times with this theta star, which is the not the true value, but the best value, kind of. We hope that it's the true value of these parameters, if the model represents reality, plus a bias. it's a bit of a problem, this equations by this first equation, by the way, because how much do you attribute to the bias, and how much do you attribute to the computer model deficiency in parameterizing the particular phenomenon? There's some issue here, but with strong priors, maybe you can separate those. And the field data are just reality plus some noise, and you learn about the noise also in the study. So these two equations are fundamental. In the original paper, there's even another parameter here, which is a multiplicative bias. Actually, we got rid of that at the beginning. The scientists actually knew that their model had a multiplicative bias. They knew that their model was 40% off, by the way. There was a recent publication that emphasized the reason why, but they knew that, and we multiply everything by 1.4 at the beginning. But it's not the best technique, but it's okay. Anyway, so, and what is the technique? As Robin presented yesterday, you're going to use a GASP. So what is that? It's actually just saying that the values at which the computer model is exercised are known, and the others are unknown, and they are normal, multivariate normal. Here we assume a constant mean, unlike in your work where you assume a drift. I mean, you have a trend, more of a trend. And the covariance function has this density, which is the multivariate normal density. So x here, dimension 4, because we have 3 thetas, and we have 1 for time. Okay, and you have this multivariate normal distribution, which is standard. See, if I continue here, so we want to interpolate the response. This is the computer model for this t theta equals x in between the design points. So in between the design point, it's uncertain, and the examples that you showed yesterday was very clear about that. You have some uncertainty in between. So you want to interpolate this computer model, and it's uncertain in between, and it's certain at the design point. So everything has to be worked out here. So one of the little problem here is that also the outputs of the computer model are periodic in time. The 0.24 is actually, it should match. Right? It's periodic output. So you cannot say that if you're far away in time, you're already far away in correlation. Okay. It's not true all the time, because if you're at the end of the day or at the beginning of the day, you should be correlated. So we had to make use of this correlation function on the circle 0.1 for the time. The time 0.24 was put into 0.1. Everything was put into 0.1, by the way, but I mean, eventually, but for the time here. So here, this complicated expression, that means that, well, this is the angle between time I and time j. If we look at the outputs of the computer model at location, I mean at inputs xi and inputs xj, so the covariance between those two. Well, for the time component, here it's the angle, there's a sine, square, whatever. It makes it a genuine correlation function. But so if you're, what is that? Is the angle, is the kind of the minimum distance between those 2 points. But we had to do that, because if not, we couldn't borrow strength across the hours at the end of the day and at the beginning of the day.
I don't understand why you do so complicated with time. Why you don't consider a 3-dimensional vector eta?
Just eta.
Yeah.
Because we want.
Why is time so complicated here? Because I mean, is it because you assume some error distribution in time when it's measured?
No, actually we don't. Yeah, there's no error in the time. Yes, that's true. Because we want to borrow strength across time as well. So we want to use information that's at a particular time, say t, to help us estimate parameters, and in order to infer what's going on at another time t prime. Because there's commonality there. We have runs for time t prime, but there's something common here. Okay, the time is different, but we want to. And if the times are close, well, it's obviously true that the computer model outputs will be close. So that's this part actually. It's saying, okay, if you're, there's a minus here, so if Ti and Tj are the same, obviously this is a 0 and therefore exponential 1, so that's strongly correlated. But, I mean, this part might put it to another low level, but at least that part would say, okay, 1, or close to 1. There's another parameter here, which is the rate at which it decays, the correlation, if times are get further and further. So there's a beta here, beta 4. Same for here, the parameters. So imagine that those are amplitudes and phase and electron density. And for each of those, there's a parameter of kind of rate of decay in the correlation function. And this is a very standard setting. Some people play with that number. Okay, but anyways, and this is the inverse of the variance, which is the precision. So the whole variability of the variability of the computer model outputs. This has to be also inferred. So if we do that, it's not finished. So here the mean would be discarded. There's this lambda eta, these betas that are just presented have to be estimated. Why is it not finished? Because the bias function, I haven't addressed it. The bias function is also modeled as a gas Brandon function as well. So it's in time as well, but it's also gas with mean 0, okay, unless the data tell us otherwise. Correlation matrix, same idea. Correlation parameter, beta 5, same idea, same modeling. The epsilon, which was the noise, the field data, the observation, the field data and the reality difference in some way, also has a distribution, which is assumed normal. And then we use the kind of the heavy technique, this Markov chain Monte Carlo technique with the Metropolis Hastings algorithm, which is a technique to carry this out. It takes some time to run. It takes more and more time if you have more parameters, more time points, etc. John T. in his paper didn't use that at all because he was much smarter than me. But this is very much a computational issue. However, there's some recent work that improves all of these algorithms drastically. I'm talking about some paper that will be presented next week at the Royal Statistical Society about Hamiltonian and Langevin-driven MCMC. Anyways, there are many improvements in those techniques. I don't know how to do that better so far, but anyways. And then you retrieve the posterior distribution of the various parameters of interest. Although, not all of them are of interest. Some hyperparameters, the betas, you're not really interested in that, but theta. So to make the whole thing run, you have to specify priors on all of this, and then look at the likelihood and carry out the MCMC. So, well, here we put uniform prior distribution over roughly an interval twice as wide as the interval which they were sampled in the simulator runs. Well, it's just saying we don't know much about those parameters of interest, the thetas. This is more interesting. You remember those betas that actually drive the decay of the correlation between model outputs. Here we reparameterize them using this exponential transformation, whatever, between 0 and 1. We put a prior on it, which conservatively places most of its prior mass on value near 1. So what does it mean near 1? That means beta has to be close to 0. That means there's no real effect. If you're far away in the input space or not, it doesn't matter too much. So there's no strong decay. Even more conservative for the bias function. So the data have to convince you that it must be the case. So it's saying, well, the data must tell you something. And then we put some other technical distributions on those precisions, which are the inverses of the variance for the computer model, the bias, and the error. And we want to put priors that say, well, we expect most of the variability to be due to the computer model, less by the bias. If the bias is enormous and the computer model varies very little, this is not healthy. And also the error, the measurement error should be small. And this is prime, unless the data convince you otherwise, but they have to really work hard to convince you otherwise. So we ran this, I repeat myself here, but we ran multiple chains. I mean, that's actually my decisions considering the time it was taking to run. And also considering the convergence issue of Markov chains. Often you run the chain, and then how do you know that you actually converge towards a certain value or a certain distribution in some way? So if you run multiple chains with different starting points, you expect things to converge at some point. So here it was quite fast, actually. About 200, 300 observations. You see here maybe what's going on. So again, Appia and Odessa, and 10 chains in parallel with colors. So at the beginning it's a bit rough, and then it stabilizes a bit more towards a certain level. Here, same thing. The first period is called the burning period, where it's not very reliable. I'm interested in theoretical results about burning periods, how to minimize them, how to know what they are, but it's not easy. I don't know much about this. Here for the theta 2, so it was theta 1. Sorry, it's not readable. Theta 2, it's this funny looking one, and this is theta 3, which was actually not reparameterized. It was the electron density all over the place. Which means totally uncertain. What do we learn from this study? Nothing. So if I go back to the histogram, so if I discard the first few hundreds as burning period, and then I retrieve what the chains tell me. On the left, Appia, on the right, Odessa, and here it's in the right units that the scientists understand, and he tells you, well, it's most likely this parameter to be around that 2.5 value. For Odessa, it's a bit different. It's more spread out. They should be a bit different, but at least we have something consistent. Theta 2, this, that. I'm sorry, I said that scientists understand. Scientists understand the amplitude and the phase. These are just the intermediary steps. Huh? And this is the electron density. That scientists understand. And this is totally all over the place. No way we can learn anything from this study. And actually, the scientists told us that they were not expecting much from that parameter anyways. For that particular type of observation, this particular magnetic drift. If I go back to amplitude and phase, so amplitude must be positive, and it is actually, also that's a constraint, but anyways, we get that type of amplitude for these tidal waves parameters. Now we can understand what's going on. The phase is very funny looking, so it's my first time ever dealing with the periodic histogram. Took me some time to see for that one. Well, we don't know if it's about 11 to 2 for this Appia location. At least we're learning something. It's obvious that we're learning something. This is deemed to be unlikely. For this particular Odessa location, more around 3. The Bayes function, which again was conservatively assumed to be a smaller part of the problem, and it should be, because unless the data tell you otherwise. For the looking one, maybe it should be smooth a bit, but not that big. The units are not that big. And now this is the uncertain prediction, as in the other example, as in the toy example. So here, I'm sorry, it's not very clear, but the observations are those circles. The solid line, the solid blue line, is the sum of the emulated computer model. There's the emulated at the best, the average actually of those. So that means that this is our best guess in some way of what is this computer model output. plus the best guess in terms of bias. Again, here I just plotted the average bias, but there's an uncertainty around this one, about this one. Okay, and the dashed lines are the define the 95% confidence interval around this solid line, and so this uncertainty is due to the uncertainty in all these parameters of interest and the fact that we have more or less observations at particular locations or things like that. Okay, there's a lot of variability. Anyway, so we should have, and we didn't cheat on this, but we should have around 1 to 2 points outside those confidence interval, 5% of the sample. I mean, roughly, it's working fine. But so that's what we get in terms of prediction, a predictor or an emulator plus some bias. Well, what is the improved emulator? That's Jonty's work, published also last year. Jonty decided to go for the expert knowledge emulation. That is, instead of letting this big machinery tell you what you should think, if you put lots of effort in understanding what's going on, and you talk for some time to the scientist, you can get something that's faster to compute and probably more accurate. So that was for another output of this model, which was the drift, and another location, and these are the computer model outputs, these lines, and these are the observations. And I think, Jonty, you found some error in the code, right?
Yeah. So this often happens when you build emulators. The first one that you build doesn't look physical to the scientist. When you take a picture like, well, not like this one, when you actually do the emulator and you explore the response of the simulator to different choices of parameters, it doesn't look physical, and that's what happened in this case. We did an ensemble of 30 evaluations, and I built an emulator, and then I said, look at what the emulator is telling us about how the simulator responds to these parameters. And they said, well, that doesn't look right at all. And then they went back and found there was a mistake in the simulator. That may have been the most useful outcome.
Yes.
But yeah, but then they fixed the simulator. And, but what we should have done at that stage is we should have redone the design.
I'm so sorry for this.
But we didn't. But yeah, this is the second set of emulations. Second set of onboarding.
So another output, and you use that technique which I advertise now, the OPE, which is saying that the emulator, so the emulator is the statistical surrogate of this computer model, is a linear sum of specified basis functions, and the coefficients are uncertain functions of the input variables. This is detailed here, so this function may be the output, and these are, say, Fourier basis for the across time, and this is the weight on those functions. And each of these functions is also uncertain. The g's are not the same. That's just but anyways, if you do that, and I'm teasing you here because I would like Jonty to explain in a future talk what he's doing now. He's improving all of this. If you do that, you can build an emulator that's tractable. So that means that here you have a conjugate structure. I mean, if you make those choices, you decided to make those choices because then you have a closed form, right, for the posterior. That means you don't have to run the MCMC. It's many simplifications here and assumptions, such as this variability must be the same, etc. Here, I think if I remember, you put actually exact numbers. You didn't, because you could do what people do, which is hierarchical modeling, where you let the data help you tell you what are those numbers, inverse gamma here, whatever. So anyways, if you do that, you can get, I'm showing you the picture here, you can get some good emulator, and when you compare with the actual runs of the model, when you leave one run out and you try to emulate that particular run, it matches quite well. Or if you learn one step ahead, it is learning with very little information. It's very uncertain, but then it's better along the way. You get better results. So that's another type. So now I want to wrap up and talk about some issues here. The design was one big issue, and And I say, well, maybe sequential design. Maybe you learn about what's going on, and then you pick a point. I think Peter, you're working on this, no? I've seen your talk in Sheffield, where you pick up on Monday. Okay. So then, sequential in many ways. Let's say sequences on Monday. So how to pick another point in the right location to sample better. Another idea is to, again, borrow strength across locations. We have many more locations than just those two, and those two studies for Appia and Odessa were carried out independently. But however, you could say use position as a covariate. How do you do that? Modeling outputs as well together, the drift and this D and H and other outputs together to borrow strength across outputs. Maybe there's some paper that I missed that addresses that. Functional modeling, which is in some way a representation of the output that a bit as you did, John T. and Susie Bayari and Dave Hingdon published on this, where the curves are entirely, they are totally modeled by a basis of coefficient functions, say here wavelets or here principal components, curves, functional principal components. This idea that Robin suggested yesterday to combine high resolution or low resolution experiments or accuracy experiments. There's a paper that I advertise here. Sequential design, we just talked about it. And the functional modeling, well, again, if I follow this idea of curves fully, so many outputs actually surfaces. Or even 3D outputs, if you think of climate models. How do you go about this? So I have a suggestion here to parameterize those surfaces, because I've worked on this in another setting. It's not linked at all to computer models, but if you have a network of observations distributed on a set of locations, you can try to model them with bivalent splines, which are the equivalent of splines in one dimension. When you have knots, and in between it's usually polynomials and they're smoothly related, it's triangles. Right? Instead of talking, I can show you just that picture. You recognize roughly the United States with a simplified Florida and Texas and so on. But anyways, that's the way we parameterize these surfaces, obtained through a network of stations scattered all over the US, which is the network of the EPA stations measuring ozone levels, ozone concentrations, about 1,000 of these. And then you design such a triangulation, and this is a difficult step, I understand, but once you're done, what is it, those splines? It's just inside those triangles, it's polynomials in X and Y of a certain degree, and in between, at those edges, it's just continuous, or even has derivatives up to a certain point. Finite elements is a particular case of that, for example. But finite elements are quite are not smooth and a bit simplistic in the triangle. It's just linear. So that's a way to do that. And I was thinking about it for example, a network of temperature station over a continent. If you want to calibrate, say, a climate model against observations for a particular continent, that's maybe a way to model the output and the observations. The output is easier because the computer model gives you many things, but still. But the observations are usually located at scattered locations, and that's a way to maybe represent that particular those types of observations. So there are many ideas, and I hope you will be interested. Thank you. Yes?
To go back to the phenomenon itself, I think you said it's well, the magnetic perturbations, but they're due to atmospheric tides.
Yes.
So you can expect that the tides are pretty large-scale coherent, etc.
That's a good point. Yes.
I mean, it's a crucial question in relation to your spatial sampling scheme. I was quite struck by the 20 or so stations that you showed on that map. I think the sea level people would like, and it's such an even type of distribution. On the other hand, they aim for something like 300. Even though sea level is a fairly integrated parameter, there are some things which vary all over the place. I was just a bit sort of other things in the way of ionospheric disturbance. We expect to have very small scale results.
This is
as wide coherent.
yes, yes. Yeah. So in the ocean, you say you have sea level buoys or things like that? Huh?
No, coastal
Coastal.
gauges measuring the sea level.
I heard about the Topex Poseidon satellite, for example.
Oh yeah, there's
That's
that as well. Yes,
yeah, that's very
not
serious.
global coverage, but occasional.
Oh, occasional.
Well, you only get past every 10 days or something, so longer period than storms.
Oh, well, I didn't know that. I was expecting sea level variations to be of longer time scale.
Well, mean sea level.
Mean
Yes.
sea level.
Any one measurement from the satellite altimeter
Mhm.
is contaminated by anything that's happening.
So, say over the Pacific, how many stations or how many buoys do you expect to have? I mean,
Well, the altimeters have to be calibrated by land-based gauges, really. Well, there is some discussion about using GPS on boards to estimate sea level rather than such. So mostly it's land-based. Well, that's a bit of a side question. It was about the spatial.
yeah. So if you have a network of buoys and they are located unevenly, and you want to represent the whole surface, I'm actually interested in that very topic because I'm looking at yes.
When you showed the mean, your posterior mean,
Yes. Oh, yes, yes.
it appeared to have what a sort of fairly short periodic character to it. Where does that come from?
The mean of, I mean, the emulator?
Yeah,
I mean,
it
the
was
predictor.
before the emulator.
Oh, no, it was the bias.
Bias, yeah, okay.
Yeah, the bias, this is a bit
this-
funny. Yes.
Is that to do with the length scale of the Gaussian process?
Yes, I think you're right. Yes, I think you. I look at this. It's not well fitted, right? Or it's just too much variation for. It shouldn't be like this. There's no.
It sort of violates what we expect. I'd expect it to be smooth and have a sort of large scale variability, but you
Yeah.
seem to have this sort of small scale sitting on top.
Mm-hmm.
It's a bigger problem that it's not periodic.
Yes. But the bias shouldn't be, should it?
No, because the data isn't.
Bias should be periodic.
Why? But the
Well.
data isn't periodic.
The bias
Yes.
is a statement about difference.
Yeah, no, it is the difference of periodic. Yes, it should be. Yes.
The system is periodic and the simulator is
But the
periodic, and the bias has
Is
to
the
be
real
periodic.
system periodic?
Well, why?
No, I don't. It is.
No, it is because what they've done is they've effectively done is they've averaged over a large
Yes.
number of typical days.
Yes, yes. I'm sorry, I should have said that. Yeah.
The system would be periodic.
They averaged,
Which is approximately
but
periodic.
it's approximately periodic.
The system is designed to be periodic in this picture.
Yes.
Well, the right-hand one could be periodic to the size of the wiggles. The left-hand one, I agree, is
Yeah.
definitely not.
The left one definitely.
And I'm sorry, I should have put the uncertainty. And maybe the uncertainty about this bias
Well,
is enormous.
The uncertainty aren't enormous, in which case it's not so bad.
Yes. I mean, enormous, not too enormous, because then the predictor but it's a zoom. The units are so small here compared to the. I mean, it's an order of magnitude lower in terms of units. Here you have 2, 3, and here you have 0.5, 0.3. So it's a small bias. Yes, I agree. There's some uncertainty about this, and Yes, maybe a stronger prior reflecting what you just said, that it should be smooth. It shouldn't be behaving like this. There will be some progress. Yes.
I mean, these marginal pictures are very hard to interpret, aren't they? Because in the fully Bayesian hierarchical framework that you're using, there's huge identifiability problems across the parameters.
Yes.
So, you know, a snapshot of any one parameter doesn't tell you much. You can see a cloud of all of those functions projected through all of the other uncertain parameters. It looks quite different.
Mm-hmm.
That's a good question.
Yes.
So, did you build the emulator offline and then insert it into the inference, or did you do the entire hierarchical inference in one big?
Yes, and then did the emulation. Yes.
Did you all at once, or?
No, I did after. Yes. So what you suggest is to do everything together?
No, I think that's the right way to do it. I think you
Okay.
go off into a different place, and you can structure a best emulator that you can,
Mm-hmm.
and then you insert it into the inference to the point where you would like to run the simulator, but you can't.
Mm-hmm.
But that's technically incoherent from a foundationalist point of view. Everyone does it, but it's interesting that technically it's not right.
Okay.
We refer to it as cutting feedback.
Didn't know about this.
No, I think we did it for about 20 years before realizing that it wasn't technically correct. It doesn't make any difference in practice. You can argue very convincingly that the only thing that you lose by building the emulator offline is the ability to learn about the emulator from the observations. But the fact is the observations contain so much less information about the emulator than your ensemble of simulator runs that the amount of extra stuff that you're learning or that you're ignoring is just tiny. It would make a difference to you.
Mm-hmm.
Thank you.
Thank you.